Hey there, and welcome to this is a little bonus video. I didn't get to all the notes from section 3.4 of the original lecture that we did in class on March 7th. So this, hopefully, fingers crossed, I don't get long-winded again. This should be just the last four examples. I think that's all it's going to be. Should be short. We'll check it out. So we just want to find the points of inflection. That's it, finding points of inflection. And this should be number 2 towards the bottom of your the skeletal notes that I provide for you. So 3.4, remember 3.4 points of inflection. I'm looking for the second derivative is 0 or does not exist as soon as I see points of inflection. So in order to find points of inflection, I need to find the second derivative. To find the second derivative, I find the first derivative. 3x squared minus 18x plus 24. If you need a review of derivatives, you should see an earlier video. I'll try to write a little more clearly on this one. 3x squared will have 6x minus 18 for our second derivative. How nice. Notice how each derivative takes the degree down by 1. So I will want to set my second derivative equal to 0. We can add 18, divide by 6 to find that our x value is 3. All right, so our breakup of our number line is at 3. We'll have an interval from negative infinity to 3 and another one from 3 to infinity. I'm going to put a little line down here because I don't have my chart, but we don't need a chart. We're good. Now, we're going to have test points. I'll use x equals 0 and maybe x equals 5. So with our test points, we will also need green, a value of the second derivative. So the second derivative at 0, 0 minus 18 is pretty negative. Oh, negative. So that's going to be concave down. So I draw a little like upside down. It looks like hair for one of the... Oh my goodness, I was just about to tell you about some trolls. It's my grandson's favorite movie, Trolls and Trolls World Tour. I know it. Second derivative, sorry, I won't go off on those tangents. At 5. 5 times 6 is 30. 30 minus 18 is positive, so the graph is concave up. CC up. And so we do have an inflection point here because it definitely changes. Well, let's make this pink. Ooh, pink might be hard to see for some people. So I'm going to go with a lighter blue. So here we have a point of inflection. What is that point? Remember, a point of inflection, we find it using the second derivative, but we always go back to the original function to find the value of the point. Anytime you're looking for a y value, it's always the original. We'll look for signs, like positive or negative signs in the derivatives, but we don't really ever care about their number value at this stage. The original function at 3, that is a 3 cubed minus 9 times 3 squared plus 24 times 3 minus 18. This is 27 minus 81 plus 3 times 2 is 6, so that's 60, and 12, so that makes 72. Oh yeah, 3 days, 72. We knew that. All right. The way I would add these together, I would add the positive values. 27 and 72 makes 99. And I'm going to add the negatives. 8 and 1 makes... I did all of that work and it's a 0, people. It's a 0. This is a point of inflection. All right, and that's all we're looking for. All right, and it makes sense. It makes sense because a cubic graph only has one hinge point. It has one maximum, one minimum, and a hinge point generally. Here we go. 5 minutes of problem. I think we could do this. We want to find possible points of inflection. So we find the first derivative. The derivative of 2 sine x is 2 cosine of x. The derivative of 2 cosine x is minus 2 sine of x. Second derivative. One of my classes actually made it to this example. Sorry, just totally jumped on you there. I think our 9:30 class, I think we made it to this example, the trig example. I get long-winded at my 10:30 class because I've already done it once. At least I can admit it, I guess. Our second derivative, but we'll go through it again, is what I'm saying for you 9:30 people. Or, you know, 2 cosine of x. The derivative is minus 2 sine of x. The derivative of minus 2 sine of x, this piece, is minus 2 cosine of x. Notice how they just changed signs, right? Think about that wheel of sine and cosine derivatives we have in the classroom, and what's two spots away is the same function with the opposite sign, all right? So we'll set our second derivative equal to 0. This is when minus 2 sine of x minus 2 cosine of x is equal to 0. So let's just divide by that negative 2. Let's get that out of there. Divide by negative 2, we have sine of x plus cosine of x equals 0. So this is looking for when sine of x equals negative cosine of x. So now I'm looking for when sine and cosine are same value by number, but opposite signs, S-I-G-N. And we know that sine and cosine are both square root of 2 over 2 at pi over 4. But we want the quadrants where they're opposite values, opposite signs. So that's 3 pi over 4 and 7 pi over 4 in quadrants 2 and 4. All right, so we are looking for possible points of inflection. So now we cut up our interval. We're going to start at 0 and end at 2 pi. But we won't actually use those values in our intervals, remember. We have 3 pi over 4. We have 7 pi over 4. We can use test values. Something smaller than 3 pi over 4, I'll use pi over 2. Between 3/4 of a pi and 7/4 of a pi, I'm going to use pi. And I'll probably use 11 pi over 6. Quadrant 4, I want something as close to 2 pi as possible that I actually know the value of. I'm going to bring us back down here, get some lines going. Maybe raise this up a bit so my hand doesn't hurt so much. Got to remember what colors I'm using here. Okay. So next we're going to evaluate. We want the sign of the derivative, the second derivative. So the second derivative at pi over 2. Second derivative at pi over 2. I naturally call it f. I apologize. It's named y. Y gets mad at me a lot for doing that. At pi over 2, the sign is 1. So negative 2 times 1 is a negative 2. At pi over 2, cosine is 0. So 2 times 0, so it's negative. So this is concave down. At pi, the second derivative at pi, that is not pi, that is second derivative. At pi, sine is 0, and at pi, cosine is negative 1. So I'll have minus 2 times a negative 1, which is positive. So it's concave up. And the second derivative at 11 pi over 6. We have, let me see, at 11 pi over 6. Sine of 11 pi over 6 happens to be a negative 1/2. cosine of 11 pi over 6 happens to be square root of 3 over 2. I know this because I know this. This is 1 minus the square root of 3. Now, if we want to compare sizes, remember 1 is the same as the square root of 1. And so, since 3 is bigger than 1, the square root of 3 must be bigger than the square root of 1, and therefore this is negative. Do I care what the decimals are? Not at all. I know this is concave down. So what that tells me is here with wrong color, I have a point of inflection, and I have a point of inflection because it does change concavity, down to up to down. So we know that points of inflection are at 3 pi over 4 and 7 pi over 4, but we always go back to the original to find the y value. Sine of 3 pi over 4 is, that second quadrant sign is positive. So that's 2 times the square root of 2 over 2. Cosine of 3 pi over 4, cosine of 3 pi over 4 is negative square root of 2 over 2. But I'd like to bring your attention to the fact that this is just a 0. 7 pi over 4, think about this. This is in quadrant 4. They will have opposite signs. So this is also going to be a 0. And I encourage you to check that out. All right? Make sure that those are going to be... All right, you convinced me. I want to see 2. 2 sine of x plus 2 cosine of x. Graph it. Look at that. It's concave down. Right here at 0. Now it's concave up at 0. It's concave down. All the time. Nailed it. Good job. I know you were keeping up. I know it was a good job. Okay, so now we would just want to use the second derivative test. So we have to have the second derivative to determine if there are any maxima and minima. Remember, these only happen at critical numbers. And critical numbers happen when the derivative is 0 or does not exist. So get used to seeing minima, maxima, and your first thought. That happens at critical numbers. Critical numbers where the derivative 0 or does not exist. You just need those ideas to connect for you as you're looking at them. Now, remember that square root doesn't go through there. Don't even do that to me. You know algebra. You know better than that. The first derivative. Let's see. Let's rewrite this. This is x squared plus 1 to the 1/2 power. So our first derivative, we'd bring down the 1/2, leave the inside alone, subtract 1 from the exponent, and multiply by the derivative of the inside. And you know how I feel. If we're going to use it, we have to simplify it. So this 2 and the 2 from the 2x, they cancel out. Call this simplify. Simplify. The derivative is 2's cancel out, x over the square root of x squared plus 1. All right. So I can find the critical numbers. Check it out. If f prime of x equals 0, the numerator will be 0. Always. Why is that? Just as a reminder, I believe I showed this in both classes, but I'm going to do it anyway. If we set any fraction, in particular this one, equal to 0, our first step is going to be multiplying both sides by the square root. And when we multiply the left side by the square root, what's the square root times 0? It's just 0. All right, so when you're looking for where's the derivative equal to 0 and you have a rational expression, we could deal with just the numerator. But when we're looking for, make sure I switch colors back. When I'm looking for where the second derivative does not, or excuse me, the first derivative does not exist. Now I'm looking at the denominator, right? I want to know if there's any place that makes the denominator undefined. But remember, x squared is 0 or bigger. And when I add 1 to that, it's going to be 1 or bigger. So it's always positive, always bigger than 1. And the square root of 1 or a number larger than that, that's always going to be positive. So it's never equal to 0. So we don't have to worry about this. So our only critical number is x equals 0. All right, I'm going to put a box around it, call it a critical number, because we're going to come over here and find the second derivative. Right? We want to use the second derivative test. So to find the second derivative, I have to use the chain rule inside the quotient rule. So we have low d high minus high. Now we have to take the derivative of low. But you know what? We already know this derivative. How do we know? Because it was our original function. So we already know that this derivative is the first derivative itself. No, that's not a fluke. It happens. All right, all over low squared. And check out what happens here. That radical's going away. Since I'm going to use this, I'm of course going to simplify first because I have to model good habits. Second derivative will be the square root of x squared plus 1 minus x squared over the square root of x squared plus 1. So I'm going to naturally throw this over 1. Have to deal with that. But check it out, the square root squared, I get x squared plus 1, which is always positive, so we don't have to worry about an absolute value here. Now, what do we do? What do we do? Don't make this hard on yourself. Let's go for some orange here. We could do a number of things. So I'm going to multiply this fraction in the numerator and denominator by x squared plus 1. Because when I multiply in the numerator, I'll get x squared plus 1. When I multiply in the denominator, I'll get the square root of x squared plus 1. So we have a common denominator now. And once we get a common denominator, we just take care of the numerators. But check it out, right? See how this x squared plus 1, that's to the 1/2 power. And this x squared plus 1, well, it's to the first power, right? So there's a 1/2 in a denominator and a 1 in a denominator. Those do in fact simplify to x squared plus 1, 1 plus a half. That's a 3/2 power. Yeah, it's a weird looking 3, but the x squareds cancel out in the numerator. I'm left with a 1. This is my second derivative. I can evaluate it at 0. At 0, I'll get 1 over 1. So I'm working my way backwards now. And f double prime at 0 is positive. The second derivative, positive, means concave up, means we have a minimum. So we know there's a minimum at x equals 0, and the actual minimum itself is at 0, 1. So we know we have a relative minimum at 0, put it into the original 1. So step 1, step 2, step 3, step 4 to come to our answer. Woo! Last one. It's going to go over. I was hoping to cap this one at 20 minutes. See, there's just no way I could have made this happen today. But we could do this one fast. All right, give it a pause right now. Try it on your own first. And then, okay, don't pause right now because now I'm still talking. So try it on your own first and then unpause and then get that confidence you need to get your homework. Okay, but now I'm going to do it. So, pause for real. Welcome back. I know you didn't pause. Okay, first derivative is, I'm just kidding, negative 3x squared plus 14x minus 15. I'm really sloppy with my 4s. I apologize for that. First derivative. So we need to find critical numbers. It's a polynomial. So we know the first derivative is always exists. We just need to see how this happens. Let's see. I'm looking for negative 3 times negative 15 is 45. I want two numbers that multiply to be 45 that are different by 14. We could take the easy ones, 1 and 45, 3 and 15. Oh, we're getting close. 5 and 13. That doesn't seem right. How about 5 and 9? Because I do know how to do math. And 9 plus 5 is 14. So there we go. The way I do this is I rewrite negative 3x squared. And this 14x, I'm going to rewrite it as plus 9x plus 5x minus 15. So I've expanded this middle term. It's called the AC method of factoring. You can find it on my website in Extra Practice of Algebra if you'd like to know more. Here I can factor out a negative 3x. I'm left with an x and a minus 3, right? Make sure you divide by that negative. In the last two, use the sign in the middle. In the last two, I have a 5 in common, and I'm left with an x minus 3. Nice. That x minus 3 is in common. So we'll take out the x minus 3, and we're left with a minus 3x plus 5. Remember the zero factor property? Any two things that are multiplied to zero together to give you 0, one of them has to have been 0. So if x minus 3 is 0, x equals 3. And if minus 3x plus 5 is 0, x equals 5/3. Take 3x to the other side, divide by 3. Which is bigger? All right, remember that when we're looking at these, actually it doesn't matter. All we're finding is if it's a minimum or a maximum, so I don't need to know the first derivative test, which is awesome. I was just about to go off on number line. But that's the beauty of the second derivative test. If you have a polynomial especially, the second derivative test saves you so much effort because this derivative is super easy compared to all the other derivatives that you take on a daily basis. So we can easily now evaluate, I keep saying the word easily, comparatively. So this is negative 18 plus 14, blah, blah, blah. It's negative. Negative means concave down. It means we have a maximum. So this 3 is going to give us a maximum because concave down has a top point. The second derivative at 5/3. The nice thing is the second derivative brings that degree down so much you don't even need to reach for your calculator here. I promise. Just do it the long way. Negative 6 times 5 is negative 30. Negative 30 divided by 3 is negative 10 plus 14. Positive. I do not care that it's a 4. I only care that it's positive. Positive means concave up, and so we'll have a minimum. And again, If my fingers weren't so tired right now, I just did 2 videos back to back, I would find the y value using the original function. But I'm going to also call it out of paper. That's it for today. So I kind of got caught up to today. I'm going to be recording more tomorrow morning. I'll get those posted. Ask me questions. I'll get you your web assigned questions, and I'll be on Blackboard during class time all week. March 8th, 9th, and 10th of 2022. Hit up your class. There will be a link for you.